Welcome to Shanti-Peace. In the previous videos, we have talked about the necessary and sufficient conditions for friendship. In this lecture, we are talking about the equality of mixed partial. What do you mean by mixed partial? It is known as the second order derivative, that is fxy and fyx. You know that fxy is nothing but the del square f upon del y del x, and this will be the del square f upon del x del y. It has been seen that this repeated second order partial derivatives are generally equal, but they are not equal. So in general, they will not be equal. And f of xy at AB is different than f of yx at AB. That we can see in the following examples. Before that, I want to recall what will be the definition of partial derivatives with respect to x. Del f by del x at point AB is nothing but the limit of f of a plus h comma b minus f of ab upon h as h tends to 0, and del f upon del y is at point AB will be limit of f at a comma b plus a minus f of ab upon k as k tends to 0. So here we are changing in variable x because it is a plus h to a, and we are keeping this y variable fixed. That's why it is known as a partial derivative of f with respect to x. And keeping your a fixed, that's why it is partial derivative of f with respect to y. Now, what is the meaning of fxy at AB? Fxy at AB, according to this definition, fxy at AB, so according to the definition, this will be del square f upon del y del x. This is nothing but the del by del y of del f by del x at point AB. This is also at the point AB. So what is this? It's first we are differentiating with respect to x, and then we are differentiating with respect to y. This we can write as del by del y of fx at AB. So by definition, as per this, here f is a function is nothing but fx. It is limit k tends to 0, fx at a plus b plus k minus fx at ab upon k. Similarly, what is this fx at a comma b plus k? By definition, this is limit h tends to 0, f of a plus h b plus k minus f of a comma b plus k upon h. Because here fx, so it is a partial derivative of f with respect to x. We are changing change in x is there. So I'm changing is a plus h to a, and this b plus k is fixed. That's why y coordinate is fixed. We are changing in x. That's why we have this. Substitute this value here. Then f xy at point AB, you will have limit a tends to 0. This is you have limit h tends to 0. This whole quantity is there. That is f of a plus h b plus k minus f of a b plus k upon h. Then it is fx at AB. Fx at AB, as per definition, h tends to 0. F of a plus h comma b minus f of ab upon h, the whole divided by k. So to simplify this, what we will get is limit k tends to 0. Then again limit h tends to 0. If I take this limit h tends to 0 here and limit h tends to 0 here, that I will take it out from this, and so you will have f of a plus h b plus k minus f of a b plus k minus f of a plus h b minus minus plus f of a b upon you will have h. If I can call this as some function phi of hk, then you will have limit k tends to 0, limit h tends to 0, phi of hk is there upon hk, where phi of hk is this function that we have. Now similarly, what is this quantity is f of xy at point AB. Similarly, what is fyx at point AB? One can give a similar argument and they can write down this as limit h tends to 0, limit a tends to 0, phi of hk upon x. Thus, what we can say is this fxy at AB, fyx at AB are repeated limits of this expression, because here we are applying h first and then k, here we are applying k first and then x. So if these repeated limits are equal, then we can say that fxy at AB is same as fy at AB. But in general, we know that the repeated limits are not equal. These quantities are not equal in general. For example, in this case, limit h tends to 0, limit k tends to 0, h minus k upon h plus k, we will apply the limit for k tends to 0. That's why it is h minus 0 upon h plus 0. So that will be 1. And on the other side, if you can apply k limit later on and h limit first, that is h minus k upon h plus k will give to limit k tends to 0, 0 minus k upon 0 plus k, which will give to minus 1. I'll see that the repeated limits are not equal in this mixed partial derivatives are not equal in the. Let's have an example for that. Example. Prove that f of xy at 0, 0 is not equal to f of yx at 0, 0 for a function f given by f of xy equal to xy upon x square minus y square upon square plus y square, as xy is not equal to 0, 0 and 0 if xy is equal to 0. So the first thing that we need to calculate what is fxy. If you want to calculate fxy, it is looking at the fx at y. First we are calculating what is fx. What is fx at 0, 0? By definition, limit h tends to 0, f0 plus h, comma 0 minus f of 0, 0 upon h. That is limit h tends to 0, f of h, comma 0 minus f of 0, 0 upon h. What is h, comma 0? Substitute instead of y, if you substitute 0, then this quantity is 0, so this limit h tends to 0, 0 minus 0 upon h will be equal to fx at 0 is 0. Now what is this quantity? Let us write down that. That is fxy at 0 is 0. That is with the limit k tends to 0. Fx at 0, comma 0 plus k minus fx at 0, 0 upon k. Now I have calculated what is fx at 0, 0 here. What is fx at 0, comma k that I need to calculate? Is fx at 0, comma k. This will be the limit h tends to 0, because we are differentiating with respect to x and the point 0, k. So it is f 0 plus h, comma k minus f 0, comma k upon. You see that x is changing and y is keeping constant. That's why limit h tends to 0, f of hk minus f of 0k upon h. What is f of xy that we have given is xy into x square minus y square upon x square plus y square. So according to this, we have limit h tends to 0, this is hk into square minus a square upon h square plus a square, and f of 0 comma k, if you put x is 0 here, so this will quantity is 0, so that is 0 upon h. So finally what we will have is limit h tends to 0, h is cancel out, so you have actually k into h square minus k square upon h square plus, and as h tends to 0, we have this is k into 0 minus k square upon 0 plus k square. So finally we will have minus k as answer, because this is minus k cube in the numerator and the denominator is 6. Finally, what is fxy at 0, 0? As per the definition, limit k tends to 0, fx at 0 comma k minus fx at 0, 0 upon k. That I have written exactly the same expression that we have here. This expression I have written there, which we have obtained. And that fx at 0 comma k is minus k that we have calculated. That's why it is limit k tends to 0 minus k. Fx at 0, 0 we have calculated is 0 here, that we have here. So that's 0 upon k, and that's why this is limit k tends to 0 minus 1. Let us calculate what is fyx at 0, 0. Fyx at 0, 0 is del square f upon del x del y at 0, 0. But that we can write as del by del x of fy at 0, 0. So first I need to calculate what is fy at 0, 0. So what is fy at 0, 0? As per the definition, this is limit h tends to k tends to 0 of 0 comma 0 plus k minus f of 0, 0 upon k. As per the definition of a function k tends to 0, this is f of 0 comma k minus f of 0, 0. As per the definition of the function, we will have this is limit k tends to 0, 0 minus 0 upon k, so that will be 0, because your function f of xy is xy into x square minus y square upon x plus y square plus x. So here x is 0, so that's why this quantity is 0, so we'll have 0 on surface. Now what is fyx at 0, 0? As per the definition, as we have seen, it is del by del x at fy at 0, 0. So by definition, this is limit h tends to 0 fy at 0 plus h comma 0 minus f of 0 fy at 0, 0 upon h, and then fy at 0, 0 at we have calculated. We need to calculate now fy at h comma 0. So what is fy at h comma 0? That is limit f at h comma 0 plus k minus f h comma 0 upon k as k tends to 0, because here derivative of f with respect to y, so it is change in y only, x becomes x. So this is limit k tends to 0. As per the definition of the function, is hk into h square minus k square upon h square plus k square. F h comma 0 is 0, so that is 0 upon k, and we just notice this k is cancelled out. So finally we have limit k tends to 0, h into h square minus k square upon h square plus k square. As k tends to 0, this will be h cube upon h square, so that is h. So finally what we have fyx at 0, 0. As per this condition, that is limit h tends to 0, fy at h comma 0 minus fy at 0, 0 upon h. We know that fy at h comma 0 we have calculated as h, and fy at 0, 0 we have calculated as 0. this is limit h comma 0, this is h minus 0 upon h, which is 1. So we can say that fy xy at 0 0 is not equal to fy x. Let's discuss another same kind. Let us done another example of the same kind, so that y not equal to fy x at 0 0, where f xy is 0 if x into y is 0, and f xy is x square tan inverse of y by x minus y square tan inverse of x by y if xy is not equal to. So in the similar way, let us calculate what will be the f xy at 0 0. So as per the definition, what is this? It is del square f upon del y del x, and that is del by del y of del f by del x at point 0 0. This is also at the point 0 0. So this is nothing but the del by del y of fx at point 0 0. So what will be the fx at point 0 0? So this quantity is nothing but the limit k tends to 0 fx at 0 comma 0 plus k minus fx at 0 0 upon k, and that is equal to limit k tends to 0 fx at 0 comma k minus fx at 0 0 upon k. Hence we need to calculate what is fx at 0 0 and fx at 0 comma k. So let us calculate one by one. Fx at 0 0 will be limit h tends to 0 f 0 plus h comma 0 minus f at 0 0 upon h, and so this will be the limit h tends to 0. This is f of h comma 0 minus f of 0 0 upon h. As per our function is fxy is 0 if x into y is 0. That means any of the number x or y is 0, function is 0. So here h comma 0 is there. So since y coordinate is 0, this quantity is 0 and this quantity is also 0. So it is limit h tends to 0, 0 upon h. So that will be gives you 0. Let us calculate what is fx at 0 comma k. That will be limit h tends to 0 f at 0 plus h comma k minus f at 0 comma k upon h, and now this will be limit h tends to 0 f at h comma k minus f at 0 comma h upon h, and as per the definition of the function, f of fxy is x square tan inverse of y by x minus y square tan inverse of x by y if xy is non-zero. So that means both the numbers are non-zero, then this is the definition. So due to that we can have h tends to 0. So this will be h square tan inverse of k by h minus a square tan inverse of h by k, and as you know that x coordinate is 0, so this is minus 0 upon h. This can be rewrite as limit h tends to 0 to h into tan inverse of k by h minus k into tan inverse of h by k upon h by k. So I have divide this h to this term and this term and taking one of the k in the denominator here. So that's why we have this. And what is this quantity now? As you know that tan inverse of x is belongs to minus pi by 2 to plus pi by 2 open interval. So this is the range of tan function. That means this tan function is a bounded function, and as h tends to 0, this will tends to 0. And what about this? The limit of x tends to 0, tan inverse of x upon x is 1. So due to that this is 1, so it is minus k into 1, so finally you will have minus k answer. Hence fxy at 0, 0, as per the definition, this is limit k tends to 0, fx at 0 comma k minus fx at 0, 0 upon k. This is exactly the value which we have calculated here, and we have calculated this quantity is 0 due to this fx at 0, 0, and fx at 0 comma k we have calculated just now, that is minus k. So this will gives you limit k tends to 0 minus k minus 0 upon k, this will gives you minus 1. Secondly, let fyx at 0, 0, as per the definition this is del square f upon del x del y at point 0, 0. So that is del by del x of fy at 0, 0. So if you apply the definition, this would be the limit h tends to 0, fy at 0 plus h comma 0 minus fy at 0, 0 upon h. So now here what we need to calculate is what is fy at 0, 0 and what is fy at h comma 0. So due to that we can calculate what is fy at 0, 0 first. So limit k tends to 0, f at 0 plus k minus comma 0 minus f at 0, 0 upon k. Now as per the definition, as we have know that fy is 0 if x into y is 0. So any one of the quantity x into y is 0, this will be 0. So this is k comma 0 is there. So this is y coordinate is 0. Here both the in this it is both the coordinates are 0. So here we have the 0 answer. And fy at h comma 0, that we can calculate as limit k tends to 0, f at h 0 plus k minus f h comma 0 upon k. So this will gives you limit k tends to 0, f h k minus f h comma 0 upon k. Now using the definition of the function, we can write this is limit k tends to 0. The function is x square tan inverse of y by x. So this will be h square tan inverse of k by h, due to the function is x square tan inverse of y by x minus y square tan inverse of x by y. So that's why we have this minus k square tan inverse of h by k minus 0, because f h comma 0 is 0 upon k. This will be limit k tends to 0. So this we can write as h into tan inverse of k by h upon k by h minus k tan inverse of h by k. Here again I have divided the same thing. I am dividing this k with this term and with this term, so we'll have this quantity as limit tan inverse of x upon x, as x tends to 0 is 1, this quantity will be 1 minus k, this quantity is bounded, and as k tends to 0, this will be 0 into some bounded thing is there, so 0 into anything is 0. So finally you will have h answer for this. So finally we'll have fyx at 0, 0. As per the definition, this is h tends to 0, fy at h comma 0 minus fy at 0, 0 upon h. Fy at h comma 0 we have calculated, and fy at 0, 0 is this that we have calculated. So that's why we have limit h tends to 0, h upon h minus 0 upon h. So this will gives me 1. If I call it, this equation is 2, and the above one with the red color that we have written, that is this one. If I can call it, this is 1. So fxy at 0 it is -1 and fyx at 1 at 0 it is 1. So that's why fxy at 0 0 is not equal to fyx at 0 0. With this we can say that the mixed partial are not equal in general. Now the question is, under which situation they are equal? Under which situation fxy you can write as fyx? That is the question, and that questions we will solve in my next coming videos. So you think over that, what should be the condition I can apply on f so it will become the mixed partial derivatives are equal. So I'm stopping here. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in a comment box below. See you in next video. Bye bye. Sayonara.